In previous lecture, we had discussed about the scheduling criterias, and we had 5 scheduling criterias: CPU utilization, throughput, turnaround time, waiting time, and response time. So we had discussed all these scheduling criterias in previous lecture. Now, coming to this lecture, we will understand the first come first served scheduling. In the scheduling algorithm, this is the first scheduling algorithm. As we know that in the scheduling algorithm, CPU scheduling deals with the problem of deciding which of the processes in the ready queue is to be allocated the CPU. There are many different CPU scheduling algorithms we have. Among those many CPU scheduling algorithms, the first come first serve scheduling is the first one. So we will start this scheduling algorithm with the first come first serve scheduling. Now let us start with this first comes first serve scheduling. As the name suggests, whichever the process enters first is served first. So therefore it is the simplest CPU scheduling algorithm, and also the process that requests the CPU, first is allocated the CPU first. Means whichever the process requests the CPU first will get the CPU first. Means first request first served, second request second served, last request last served, like that. The implementation of FCFS policy is easily managed with FIFO queue, first in first out queue. So whichever the process enters first will out first from the queue. When a process enters the ready queue, means when a process enters the ready queue, its PCB is linked on to the tail of the queue. So let me write here. Okay, assume that this is the ready queue, right? So you have processes, say 1 2 3 or P1 P2 P3, like this, if you have the processes. Okay, so this is the head, right? Because we are talking about the queue, hence this is the head, and assume that this is the tail, right? Now when a process enters the ready queue, means any new process enters the ready queue, its PCB is linked on to the tail of the queue. Tail means at this position the new process is added and its PCB is also added to the queue. When the CPU is free, it is allocated to the process at the head of the queue. Means assume that the CPU is right now free, right? So CPU is right now free. So what it will do, it will take the first process from the head of the queue. Means this P1 will occupy the CPU, right? Then the running process is then removed from the queue. Right now the running process is the P1, right? That P1 is removed from here in this queue. Now the head is P2, right? This is removed. So now the head is P2. The next process is P2, that is the head. Okay. Okay. Now the average waiting time, right? So we will understand the average waiting time under FCFS policy is often a quite long. Let us consider the following example and we will come to know. So here we have a set of processes that arrive at a 0 time and the length is given. Okay. Now all the processes are arrived at time 0. Okay. Now first in first out. So P1, P2, P3. So this is the burst time in millisecond. Burst time means the total time requested by these processes. Okay. Or we can say that the process need this much or this amount of time of the CPU. Okay, this much amount of time of the CPU. Okay, now if a process arrives P1, P2, P3 and are served in FCFS order, we get the result as shown in the following Gantt chart. Now we prepared a Gantt chart. This is the Gantt chart. This is the time of Gantt chart, right? Now the P1 process is executing first as per the FCFS policy. So P1 gets a CPU first and it is served first in the CPU. Now the P1 burst time is 24 millisecond. So up to 24 millisecond, the P1 process occupies the CPU, and after its execution, or we can say the burst time gets complete, so it releases the CPU, and that CPU is allocated to P2. Now the P2 burst time is 3 millisecond. So again 3 millisecond is occupied by P2. Again another P3 process occupies the 3 millisecond of the CPU. Likewise, if any table if you get like this, you need to prepare a Gantt chart first. So after preparing this Gantt chart, you can calculate the waiting time, turnaround time, etc. Okay. Now let us move further and let us see if the process arrives in the order of P1, P2, P3 and are served in FCFS order. So we prepared this Gantt chart. After preparing this Gantt chart, we can calculate the waiting time for all the processes. So we have a P1 process. It is waiting for 0 millisecond. The P2 is waiting for 24 millisecond, right? And P3 is waiting for 27 millisecond. So how to calculate? After preparing this Gantt chart, so this is the P1 is waiting for 0. 0 means it is waiting for 0 second. Okay. Now P2 is waiting for 24 second. After waiting for 24 second, so it is getting the CPU, and P3 is getting the CPU at 27th second. So these are the waiting time for P1, P2, P3. So thus the average waiting time means now we can calculate the waiting time of the processes. Now let me add all these waiting times of the three process, 0 plus 24 plus 27, right? So we can calculate all these. 51 divided by 3 equals to 17. So 17 millisecond is the average waiting time. So this is the average waiting time we are calculating. This is the individual waiting time of the processes. This is the average waiting time of the FCFS order processes. Okay. Now assume that if the processes arrives in the order of, right, let me say P2, P3 and P1. However, the result will be as shown in the following Gantt chart. Now we are changing the process arrival time, assuming that the P2 arrived first, P3 arrived next and P1 arrived last. So now consider their waiting time. The P2 waiting time is 0 millisecond, P3 waiting time is 3 millisecond and P1's waiting time is 6 millisecond. So as per this order, the waiting time is calculated. So these are the individual waiting times. Thereafter, we can add all the 3 processes waiting time, 6 plus 0 plus 3, that is 9. 9 is divided by 3 is equals to 3 millisecond. So by changing the order, we can see that this is substantially reducing the average waiting time of the process. Thus, the average waiting time under the FCFS policy is generally not minimal and may vary substantially if the processor's CPU burst time vary greatly. Means if the processor's CPU time vary, burst time vary, automatically the waiting times also varies. But usually the average waiting time is always greater in FCFS. Now moving further, the first come first serve scheduling algorithm is non-primitive. It is not primitive, it is non-primitive. So first come first serve scheduling algorithm is non-primitive. So why we are saying non-primitive? Because uh, until and unless one process is in the CPU completes its execution, the CPU will not allocate to next process. Therefore, we are saying it is non-primitive. So once the CPU has allocated to a process, that process keeps the CPU until it releases the CPU, or either by terminating or requesting IO. So the meaning is clear. Non-primitive means once any process gets the CPU or CPU has been allocated to a process, that process keeps the CPU until it releases the CPU. So after releasing the current process, the next process can occupy the CPU. So therefore we are saying it is non-primitive. Now FCFS algorithm is thus particularly troublesome for interactive systems. Means it is this algorithm particularly creates the trouble for the interactive system because it doesn't interact with all the processes at a time, or we can say concurrently. It cannot interact to all the users. So one user is accessing, other has to wait. So therefore we are saying that particularly troublesome for interactive system, where it is important that each process get a share of the CPU at regular interval. Means that each process get a share of the CPU at regular interval. So in time sharing or interactive systems, where each process will get a share of the CPU. Share of a CPU means every process will get a some amount of time. But in FCFS, so it you can't get a share of the CPU. It is possible in RR, round robin scheduling algorithm. It is possible, not in first come first serve. So it would be disastrous to allow one process to keep for an extended period. Means any one process is executing for a longer period of time, so we can say that it is a disastrous. So it would be disastrous to allow one process to keep the CPU for an extended period. So we cannot uh, put one process for a longer period of time. So it create a very disastrous, because others process are waiting, so those cannot be executed until the current process releases the CPU. So therefore this is the, we can say, the drawback of this first come first serve. Okay, why we are saying it would be disastrous to allow one process to keep the CPU for an extended period, because until in FCFS, until the current process releases, as we discussed here, the CPU The process keeps the CPU until releases the CPU either by terminating or by requesting IO. Means if the process gets terminated or it is requesting for IO, then only it can possible to get the other process. The CPU can get the other process, otherwise CPU can't get by the other process. CPU is dedicatedly assigned to a currently executing process until its burst time gets completes. So this is from the first come first serve scheduling algorithm. So the point is, first come first serve scheduling algorithm is a non-primitive scheduling algorithm, one of the simplest scheduling algorithm, and also it works on FIFO queue, first in first out queue. So this is all about the first algorithm of CPU scheduling, first come first serve scheduling. So in the next lecture, we will understand few more examples on this first come first serve. So thank you for watching.